Can you hear me? Okay. So I'm going to try talking up here because I sort of want to have a conversation with people. Unfortunately, I didn't memorize my slides, so I'm going to keep looking around. Sorry about that. So I guess we should get started. That's me. And I cannot draw, but recently the internet taught me how to draw an owl. And I want to share it with you. What you do is, in the first step, you draw 2 circles. And then you draw the rest of the damn owl. Unfortunately, my talk is very similar to this illustration, and this is why I'm not going to show you code. Because my code would look like something from the left or from the right. And neither of them is very useful to you if you already don't know how to draw an owl. This is my talk. CRUD is dead. It used to be called rest is dead, but it turns out that rest is just CRUD over RPC, so why limit ourselves? We'll call it CRUD is dead. We'll talk about different kinds of CRUD. But I didn't want to give a negative talk, so where I just talk about all the problems we have with CRUD. So, in positive fashion, we are now going to save ourselves from the post-apocalypse. This talk is really about data-oriented architectures, right? And data-oriented architectures is a really fancy way of saying that all of the data flows in one direction. So, when you're looking for the source of truth, you just look all the way to the left, and then anything to the right of that is some derivation. Simple enough, right? Most really good ideas, once explained, are really simple. This talk is also about information systems. This is my talk, so I make up the definitions. The information system is any kind of system that accepts data from outside, external, stores it, and then at some point later in the future, answers questions about the data. So basically anything you do online, right? Your bank account, Twitter, Facebook, any kind of business applications, these are all information systems. Most of you are probably working on information systems. Google Images is an information system. When I send it a query, it gives me back a result. Fair enough? This talk is also about decoupling. But content is probably not what you think I mean, because I want to go back to the basics. And I want to tell you about how reads are independent of writes, and neither imply storage. And by storage, I don't only mean the physical kind of storage of physically storing these bytes somewhere in memory on disk. I'm also talking about orchestration. There is no reason why reads and writes have to be constrained to be orchestrated together, but often we build our systems this way, and it creates unnecessary coupling. When we remove this coupling, we get a lot of nice properties out of it. So now I've got to talk about the 2 hard problems in computer science, right? This thing has been repeated ad nauseum. Everyone knows it by heart. What is it? Seriously? Nothing? Nobody? Okay. It's caching, naming, and off-by-1 errors. Right? You guys gotta give me something. Seriously, we're trying to have a conversation here. Okay, what is the problem with caching? Thank you. And what is the problem with naming? The problem with naming is that usually we don't understand the problem we're trying to solve. So we name it incorrectly. And the question is, what do we put in this 3rd thing? I like to call it dissonance. It's something that's really important, but we don't talk enough about it. Dissonance is this idea that everyone at a biological and chemistry level, the way we understand the world is we build mental models, right? So we build a mental model about how we think a system works, and after that point, we interpret the world based on these models. And we do it automatically, and we do it subconsciously. And every time there's a bug in your system, or a user complains that something's not working, or it's slow, or all these other problems that people have, it is nothing different than the fact that they built up a model of how your system's supposed to work, based on their life experiences and how much you told them about how the sausage is made. And at some point, they hit a bump, because they did something in the system, and it didn't match their model. But developers, we're no better, because the languages we use, the libraries we use, the systems we build, automatically and subconsciously influence the kind of mental model we have in the world. And when libraries don't work the way we want them to, we blame the developer of the library. But the developer of the library is blaming us because it was never meant to do that thing that we wanted it to do, right? So I want you to really keep this in mind. Cut out. Okay. I want you to really keep this in mind because when you see a weird programming language or a weird paradigm or a weird library, weird just means that it's different from what you have been used to. It doesn't mean it's wrong. So caching, naming, and dissonance. These are the hard problems in computer science, and it turns out that immutability changes everything. Notice I don't say solve. I don't say solve because I hate that idea. I hate people trying to convince others that immutability is something we need to do, because it sounds like a goal. It sounds like an end purpose, and it's not. It's not. Immutability is a gateway drug. It's an enabler, it's a prerequisite. There's no reason to add additional constraints into your system just for fun. The only reason we do it is because as soon as we have immutability, we get a lot of other nice things. So you see, me trying to convince you about immutability is stupid, because I'm just assuming everyone wants immutability because there's a lot of nicer things out there once you have it. Which brings us to CRUD, because CRUD is not immutable. If you have immutability, you don't need CRUD, because all you have is create and read. Updates are just new facts we add into the system that say that something has changed from X to Y at a specific point T, right? Same thing for deletes. Deletes don't exist because a delete is a retraction. It says from this point forward in time, this fact that was true is no longer true. But at some earlier point in time, it was true, and we can't ignore that fact. And once you have immutability and this idea, all rights become ordered. Because if you don't have ordered rights, you have chaos in your system and you can't reason about it at all, right? So we just assume you have to have ordered rights. But reads also become idempotent because they can never change. You can call the same read many times and it'll do the same thing because it has no side effects. It also happens that once these cases are true, you have time travel because a read can go back in time and pretend it's an earlier time and space and find out what exact value would have been if I had read it at that point in time, right? You get all this stuff for free. It also turns out that there's always that one guy, there's probably one in the back of the room, that says, this is all nice. This is all nice and fine, but this is not the way the world works. What about performance? So I want to address that issue very quickly, in a very small time and space, by talking about relational databases and we use them in production. This is, Postgres, but it could be MySQL, Oracle, whatever. It doesn't matter. It's always the same. We always want more performance because the things are too bloody slow. So what do? We usually add some kind of replications, right? So one database is not enough. We add master and slave, master writes, slave reads. Awesome. How does the slave find out what is the new master? Well, it turns out there has to be a synchronization process. And guess what? Databases use immutable strings of events to tell these slaves about data. Database maintainers have figured out long ago that immutability is only going to scale. So even though they pretend that there's this big immutable state that you don't have access to, they don't do it internally. Internally, they use immutable data to send events down the stream. And that's by the way, is why replication is good. It works because it uses immutable data. Similarly, secondary indices. We use these every day, right? Whenever something's slow, let's just add an index. The only reason this stuff works, and the only reason we trust it, is because the database works very hard to keep two pieces of data that are completely separate, always in a state of, they're always the same, right? So they work really hard to pretend there's immutable data down the stack. And you trust it so much, you don't even think about that fact. Because indices are a separate piece of data somewhere. If you didn't trust your database to always keep it immutable, and always keep it the same, you wouldn't use indices. That's why it gets a smiley face. On the other hand, materialized views don't get a smiley face. Materialized views, in theory, are a way for you to write database caches that will automatically update. The problem is that it takes a lot of computing power, and it's a really crappy API to it, and basically you're limited by the kinds of things your SQL query can do. And even worse is application caching. Because as soon as you introduce application caching into your stack as a way of fighting performance issues, you're basically saying, there's this big, beautiful database, and I'm going to pretend that I can somehow control it. And I can always invalidate the cache at the correct point in time and everything. It's always wrong. Nobody has deployed application caching of databases to production and not regretted it later. I hear no arguments, so I'm going to assume you agree with me. This isn't how databases work in production. The problem is that they pretend that we have this immutable stack, but they use immutable data inside. This is how it should look. They should just give us the API where we can give it a stream of data. And I don't want to talk about this even further because there's a much better talk by a much smarter person, Martin Kleppman, who talks exactly about this stuff. And he goes into a really big detail, and he has wonderful slides because he can draw, unlike me. Right? So this is your first homework assignment. So let's get back to information systems. I posit to you that in order to build any sort of information system, you only need three things. Data, data transformations, and queues. That's all you need. Does anybody disagree with me? I know I hear silence, but I really want you to study this slide because everything that comes after this is either very easy or impossible to understand. You need to really believe the fact that if you have data transformations, and those things are immutable, and you have a way of talking about systems that is nothing else than a way of taking queues and pushing data through them at a specific rate. This is all you ever need to design any system, architecting system. Everything from the way big data stacks work to how your web server runs to the way your processor works is this. This is all you ever need. Give me a heads up that everything is fine. If you have any questions, now is the time. And yes. Show me the code. Okay. Later. So let's talk about data. Data in systems comes in two varieties. Raw and derived. That's all you got. Raw data is any sort of data that comes external from the system. So if some data comes into the system and I forget about it, I forget to write it down, I lose it, I will never get it back because it came external. Derived data is everything else, right? It could take a long time to recompute it, but in theory, anything that's derived, I can just delete it and recreate it perfectly. So it turns out that in our systems, almost all our data is derived, but the raw data is very important because if we lose it, we can't get it back. That brings us to Lambda architecture. Who has heard of Lambda architecture? These two bozos in the front. Okay, so hopefully we learned something. Let's pretend you're Spotify. Who has heard of Spotify? Okay, so Spotify uses Lambda architecture to some extent. So the idea is that you have a database and you have raw data. I've used photos of people I know, my coworkers, because this way I can embarrass them online. So your Spotify and events come streaming into your system. I listened to some album, someone else followed an artist, or maybe they favorited an album, or maybe they actually released a cover song from Iron Maiden, or maybe as soon as that guy found out that that guy released a cover song, he started following him. These are all events that come external from the system. If Spotify was to lose them, he would never get them back again, right? But what's really interesting is that once you have this kind of raw data, everything else you can derive from it. You can find out who are your favorite artists, you can find out how much money a specific artist made, you can find users that have similar listening interests to me. Using that very basic kind of unstructured data that's flat, you can build entire graphs of knowledge. And so that's what Lambda architecture is. Events come to a queue. Everything starts with a queue. Events come to a queue, which then lands in a database. Since this database has no interest in doing any queries, it's an append-only log. Its only role in life is to store data at the end of the list as fast as possible and as durable as possible. So spread it across multiple nodes, multiple regions. However much money you've got and how important your data is depends on your solution is going. And that's the end of that side of the stack, because then a query comes in. Give me all of my favorite songs. It goes into a queue. Remember, web server is nothing else than a queue, right? And after it hits the queue, it gets read at some point by the Lambda. And what the Lambda does is it says, give me the entire history of the world. I need to find your favorite artists. And it starts scanning that entire event stream and aggregating and counting, and it returns a result. And this is the only thing you ever need to know about building systems. All systems work like this. Anything more complicated is just unnecessary. So there's only one problem with this. If your Spotify petabytes of data and you expect a 10 millisecond response time, this will never work fast enough. It's too slow. But the idea is solid, it's just that it's too slow. So what do? We're developers. Let's add caching. But caching has a really bad name because of caching validation. But remember, we are now in an immutable land. And in immutable land, caching can call materialized views. It is the exact exact same thing, it just has a lot better PR. So materialized views aligned architecture is these things that they call a serving layer. So we know what kind of queries users want to make, so we're going to build caches that serve those kinds of requests. If you need to do a full text search, let's put Lucene or Elasticsearch in here. If you need to do some kind of aggregations, Redis, Cassandra, ElephantDB, whatever, it doesn't matter. The point is, every time your business changes or you need to add features, you add new service layers, you add new serving layers. You can do it at any point in time, especially like if you introduce bugs or something, because anytime it changes, you just drop it, take your original data, and process it again, right? As long as you've got raw data, you can redo this every single time. Like you can do this every 5 minutes, whatever, it doesn't matter. This is actually how lambda architectures work in practice. They batch process a bunch of stuff, and this stuff is immutable, it just serves for reading. And then every time this batch operation finishes, it starts doing it again. In practice, if we're talking about big data stacks, that batching layer is usually Hadoop. Right? There's no particular reason why there's other solutions. I want you to understand the idea of one that's specific implementation detail. So Hadoop, anybody has heard of Hadoop? Or, MapReduce in general. Okay. So we've got input, and then we split the input into X amount of nodes, however big our data sets are. And then we apply some mapping operation on it. For example, here we just color all things green. And then a reduction. So in this case, we find this function finds all the unique shapes by first coloring them and then aggregating them correctly. Right? So that's Hadoop in 20 seconds. So that's our lambda architecture. Events come in, they automatically, the first thing that happens, they get stored in the database, they're all APPEND-ONLY log, because if we don't do that, we lose it. And then at some point, this batch operation is going to finish, and it's going to start up again, and at that point, it's going to regenerate my new data. Now, in many cases, this is enough. But there are cases where it's not, because every time, the serving layer is always behind in time, right? Sorry, I missed the slide. That's where the queries come in. So we're always behind in time. And oftentimes it doesn't matter. Oftentimes it doesn't matter. If we need to, if a user has a reporting for, once a day reporting, if it takes 2 hours to do this big calculation, it doesn't matter. If we have 5-minute processing times and Twitter only shows the last 10 minutes, whatever, it doesn't matter. But sometimes it does. And the thing is, when it does, what do? Well, you add complexity to your system. You wanted complexity, here it is. We do something called a speed layer, because these guys are really good at PR. The speed layer is the exact same thing we just said, but it has a very different API. This processing layer is a streaming API. So it doesn't do batch, it does streaming in real time. Usually, if we're talking about big data stacks, this is Storm. And Storm is just something which lets you build topologies. And topologies consist of these spouts and these bolts. Spouts are for data, and the bolts are for computation. Notice again, we see that pattern. Everything one-way flow. This is the only thing that scales, one-way flow. So this is our final architecture, We have data. It goes and gets processed on the top. At the same time, it flies into the streaming API. Sometimes the kinds of things that need to be streamed are not the same kind of data that needs to be batched, right? And then our system is a little more complex because when we ask questions, we need to ask the serving layer. But we also need to ask the speed layer, right? We've got 2 points of information now, 2 sources of truth. And we want complexity, so here it is. Because either the client needs to be able to figure out how to merge this information, or it's a proxy between the client and the system, right? You don't get anything for free. So this is intermission. Because I want to talk about a couple of things that are not exactly definitions of architecture. So I didn't know where to put it in, so it's just going to be in the middle of my talk. The first thing I get is, I have to get this question. What happens with this data? It's infinite, right? You can't have an infinite amount of data. It doesn't work. Well, it turns out it does work. All the big players, LinkedIn, Facebook, Twitter, whatever, they all do it. Kafka is LinkedIn's solution, right? They said, let's build this APPEND-ONLY log that stores as much data as we need. It's only a question of money. So if we need 7 days worth of data, and it takes 10 petabytes, that's exactly how much storage we need on S3, right? The more data we need, we just push in more money. But at some point, the company's going to run out of money. So idea of what do you do with the data you don't need? Well, you can either truncate it or you can compact it. Truncation is just, our business domain says we don't need data that's older than 7 days, or older than a year, or older than 10 years, whatever. We just don't need it, so let's just throw it away. And basically you just configure copy. You say, throw away all data that was longer than 7 days. But sometimes you want the old data, but you don't need all of it. So for example, let's say LinkedIn groups things by user profile IDs and says, you know what, we don't care about email changes. Let's just keep the most recent email change and throw away the old ones. So this is a form of compaction, it's a form of garbage collection. What you're saying is, some data is not important to my business, I'm just going to keep the most recent event. Notice in the worst case scenario, if you compact everything, you just get a SQL database. Because you just get the most recent version of all the changes, right? And you were able to store that somehow, so you are able to store this somehow. It's the same amount of data. Holy shit, sorry. Okay. That was the wrong one. But the nice thing about systems that work well is they give you options. If the architecture is simple enough, then every part that doesn't work the way you need it, based on your business domain, you can just change it, right? This is a very good property that you need to look for whenever you decide to choose technologies. Do they give you the option to choose? Now they want to talk about concurrence models. Who here has heard of the actor model? Or message passing? Those two small talk guys and one guy in the back. Awesome. Okay, what about CSP? Even less hands. Okay. So this is an actor model. You have objects in memory or on servers or whatever, it doesn't matter. You've named processes. And named processes need to do work, and the way they do work is they communicate with each other. So they send messages to each other. So this is what Erlang and Akka and all these systems do. But notice this is also object-oriented programming. Object-oriented programming says we've got a lot of object instances that we know because we've identified them, we put them into we pointed to them, right, in memory. And A, in order to do its work, it needs to know that E and F exist in the system because it needs to send it a message. It needs to say, send this data to E, right? So those things are identified, but the messages are anonymous. CSP is the exact opposite. Because CSP says that the processes are anonymous. The processes are anonymous, but the channels are defined. And that's how things communicate with each other. They don't know about them. They don't know about each other. What they know about is that there's two channels in here, A and B. And this guy, when he wants to do work, he knows that if he puts it on channel A, someone at some point will read it off and do the work that he wants. So, in theory, they are two sides of the same coin. In memory, you've got processing and you've got messages. But in practice, it turns out that CSP is a much more elegant way about reasoning about systems. For some reason, we are able to understand defined channels better than we are able to understand defined processes. Examples of this are Golang and core.async, right? So I want you to think about this the next time you build systems. Queues are important, and named queues are even better. So what about NoSQL? We don't want all the baggage of SQL mutations, but we want that convenience of declarative queries, declarative processing. So I wanted you to introduce to you two query engines that you may have not heard of, but probably should. One of them is Cypher, which is a SQL-like language, or Neo4j, which is a graph database. I know it looks a little like ASCII art. I know that. But the thing about it is, it's a query language that has this idea of nodes and vector and edges, right? It's a graph database. And what happens is you can define in your query a shape that you're interested in, finding inside the graph. And what it'll do, it'll really quickly go through the entire graph and pull out the parts that are interesting to you. This is something you can't do in a relational database because you can't do infinite joins and you can't do graph traversals. Here in this case, starting with some specific node to make a good example, I want you to find everyone, so find some node that knows me, that also knows somebody that also happens to know me. So I want you to find connected neighbors, right? I want you to find friends of friends that happen to also be my friends. And take a look. data log is something I want you to be aware of. Because data log is really cool. Data log is really old. It's like from the 70s. Like almost good ideas that came from the 70s. When you squint at it, it looks like SQL. Give me a title of some entity E, and the entities I'm interested in, I'm looking for the title of this entity, and the entity has to have a year 1987. Who here has done Prolog in school? Or any kind of logic programming? Data log is a subset of Prolog, so that means it's a unification system. Wherever you put variables, the computer will intelligently figure out what possible things match, and it will return all of them that match all the rules. So this is a simple example. This is one where we see graph traversal in progress, right? We have a movie, The Matrix, and the movie has cast members P, and for each cast member P, it has a name attribute, and I want you to return all the names, right? And this goes infinitely, and it works really, really fast. Of course, I'm showing you Datomics, or Clojure's version of Datalog, and what you see there on the bottom is Clojure code being run. So this is the problem we had with databases, that materialized views were limited to SQL. Here, you're only limited to whatever you can do in Java. And we've got aggregation, and we've got a full API, and we've got other tons of really nice things. This is your second homework assignment. It's called LearnDatalogToday.org. It's going to take you 2 hours with your favorite alcoholic beverage to go through the entire book, along with, watch out, interactive exercises. Imagine if I told you you can learn all of SQL in 2 hours. Yeah, that's what I thought. So let's talk about Datomics, since we're talking about data log. Datomic models their entire system based on this idea of, sorry, I'm just checking my time here. So Datomic models its world with the notion that reads and writes are different things and storage is a different thing, right? So it's an actual implementation of this really good idea that we had earlier. So facts that come into the system are flat. They're called datums in Datomic. It's just some entity ID. It's the idea of separating identity from state. So I am as a person am me, right? If we want to get really philosophical here. But I have many attributes. I'm wearing a specific sweater that has a specific color and so forth. But all these things are understood that they all belong to me because that's the way our mental model of the world works, right? We all have this idea of identity, and state is independent of it. Because if I change my clothes tomorrow, I'm still going to be me, and you're going to know who I am, even though all my clothes are different, right? So when you model systems, all you have to do is you have to identify that there's some kind of identity that I'm interested in, and it has a certain attribute and a certain value at a specific point in time. That's all you get. That's the only thing you need to model every kind of thing in your system. Because you can, based on a flat structure, you can create a very complex graph that's also time independent. And on the query side, we get data log, right, which I just showed you. So we have a much different writing model and a much different reading model. But it's not only conceptually, it's also physically. Physically, Datomic is 3 different systems. It's a transactor that's responsible for writing data. It's a storage system that's responsible for keeping your data safe. And it's a set of peers that are responsible for handling the queries, so handling the reads. So it's 3 completely separate systems, and like all good systems, they give you options. And the point is, depending on what your use case is, you might have a lot of data, so you need to expand your storage. They don't actually do storage. What they do is that they do a storage plugin. So this thing can be S3, it can be Cassandra, it can be MySQL, it can be DynamoDB, it can be whatever you want it to be. Because you choose the storage structure based on the kind of promises that those guys made to you about different kinds of properties of the storage, right? Dynamo has a different kind of characteristics than MySQL or Oracle or Cassandra or HBase or whatever. You have to decide on the storage engine because you know best what's good for your data. They don't care about it. Datomic doesn't care. The transactor is interesting because the transactor can only be one. Now, if you need a high availability, yes, you can put many of them to be, hot reloadable. But at any one point in time, only one of them is working. And the reason for this is because I think I told you earlier, most business systems, most information systems are interested in ordered writes. I don't care how much you say you want to be scalable, at the end of the day, nobody understands multiple universes. We're just not that smart. So we need to have ordered writes at the point of transaction. Right? This is the only way you can have transactions. Because things are ordered and there's only one person responsible for them all. But the nice thing is, since the only responsibility it has is to accept data and write it out as fast as possible, it turns out that you can scale this really, really well, vertically. I mean, it's not infinite scaling, but nothing's infinite, right? It's going to scale much better than whatever you've got. Trust me on that. And then there's peers. And the peers are the readers. The queries that come in read from the peers. I just realized I have some slides for this. So that's where the data comes in. It gets written to storage, and then storage pushes the stuff out to the peers. In the meantime, notice the way the storage pushes stuff to the peers. This is very similar to Lambda architecture because it does this in a batch process. If you lose all the peers, you don't lose the data, and it can recreate everything. But in order to keep it real time, it turns out that the transaction can also send data directly to the peers in the meantime. And the reason all this works is because it's all immutable. Because if you have immutability, you don't have a problem with ordering, and you can send things from different directions. And because it's all immutable, it turns out that the peers can cache the data without cache validation issues. The data is always true. So when it comes time for talking to the database via data log, oftentimes the peers don't even talk to storage. They've already cached all the data for the kinds of queries they're interested in. And on top of this, you can add memcache or varnish, whatever. You can add caching on caching on caching. Because you have immutability, all these problems just went away. Let's talk about memory. I know what you're thinking. Memory is the one thing you can't make immutable. Clojure is done throughout programming, and mutexes and all that fun. Two very sad faces. Okay, so we know programming with threads and mutex is hard. But most people who don't write production software don't realize how hard it is. Because if you have a bank account, that classic example of withdrawing something from an account where you have to subtract from one and add to another, it's very simple. Let's just put a lock on it. But that's not how the real world works, because when you have multiple processes, multiple systems communicating at the same time, you can't just lock a critical piece of code. You need to lock all the parts that are interdependent, interrelated with each other. This is why programming with threads and mutexes is hard and why nobody gets it right. Right? Because the only way to get it right is to simplify the system to the point where you can reason about it. And then it's just a really simple system. But there is a solution. This, surprisingly, is not from the 70s. This is from 2005. I think thereabouts. Software transfer memory. Hands up. Anybody? Okay. It's interesting that I always get a couple of hands, but they're always from different people. Software transfer memory is saying, let's make ACID transactions in memory. Now, obviously, you can't do D, because you can't do durability, because it's in memory. If you turn off the server, everything dies, right? But let's get close enough. Let's do ACI. Let's do atomic, consistent, isolated system. In-memory processes. And the way it works is it says, let's pretend for a minute we have immutable data. And if we have immutable data, we can create transactions. And transactions say that this thing needs some piece of memory, and this thing needs some piece of memory. If this thing needs a piece of memory but it needs a read-only, we're very optimistic. We're just going to give that data. In fact, if that thing is writing to data, writing to this memory block, and this thing is writing to this memory block, we're also going to let it do its thing. This is the difference between STM and classic mutex locking. STM is optimistic locking. They're going to let you do everything. And the reason they're going to let you do everything is because when it actually comes time to commit, they have a transaction log. And they can say, you know what, you created a very complicated process full of different things, but over here in step 99995, it looks like you accessed a memory that actually had changed in such a way that it impacted your thing. Because it's not even enough that you read from something that changed. You read from something that changed and used that value to update something else that happened to change that first guy was going to use. These are the kinds of things you just can't model, you can't reason about. But if you let the computer do it, computers are really good at this. And the only reason STM works in practice is because we have transactions that are retriable. And this is why you need immutability. Transactions are idempotent because it turns out that a transaction, so a write into memory, may happen more than once. Because you try to do it once, and and then STM says, sorry, someone got there first. Okay, I need to roll back, I need to retry all those steps I just took. So none of this works if you don't have immutability. This is also why in Clojure, when people ask me how to do things, if the amount of data that you have, it fits on one machine in memory, I'm just going to tell you use Clojure. In the sense of, don't use in-memory databases, don't put it into storage, don't try to log transactions and so forth. You don't need any of that, because it turns out Clojure has data structures that are immutable, and has a very extensive sequencing API. So it has all these kinds of things that you need to intelligently transform and derive data. And it has an STM. And the STM says, don't worry, just put this thing in memory, I'm going to take care of all these different issues of blocking and transactions. I got your back, yo. And then you've got data log. And data log, as in you can write data log without datomic database. You can just do it in memory. You can do it on collections. As in you have a hash map of hash maps of the list, and you can present it to graph, and you can do graph searches on it. And on top of that, you have core logic, which is actual implementation of core logic. Right? You have a lot of stuff at your expo that you can use. So this is why I'm such a fan of Clojure. But we've got a couple of minutes, and we've been talking about backend the entire time. I want to know about frontend. Because frontend is not something that is automatically solved if you have a one-way data flow. You may have heard of Facebook. They have this thing called React. And the reason why they built React is that they realize that DOM manipulation is slow. Right? How many people are familiar with the problem with React? All backend developers, I see. So the problem that we're facing is that just writing to the DOM is very slow. And so the way we speed up websites is we don't do it very often. So it turns out we keep an exact copy of everything that's happening in the browser in memory in JavaScript. So there's a JavaScript version of the DOM that's a one-to-one clone of the one in your actual browser. And it turns out that this way is faster. It's not intuitive, but it's faster, because you do all your operations on the virtual DOM that's in memory, and then once in a while, or specifically 60 frames per second, right, whenever your animation frame kicks in, React will figure out, will take your entire DOM, and it knows what's in the actual browser because it controls it. And it's going to say, it's going to do a diffing algorithm, and it's going to be really fast, and it's going to operate, and it's going to, after it figures out what has changed, it's going to create a batch operation that's optimized per browser. Now imagine doing all of that in Backbone or Ember or whatever. It doesn't matter. You can't do this stuff by hand. This is what computers want you to do, right? So this is how your application looks like if you do this. That's your actual browser. You create, or let's start with the left, because remember, data flows one way. So you start with data. And your data is your business logic. And what you do is you generate a virtual DOM. So you generate what you want your web page to actually look like without any idea of what the web page actually is on the browser. And then what happens, React.js kicks in and makes it happen, right? It just takes your thing and it makes it happen in the browser. And so they solved this problem. And so they were done, right? And this is all you need to do. Well, it turns out not, because there's a second problem in front-end development, and it's called 10 milliseconds. What is the problem? Man, you guys are giving me nothing. Okay. The problem is that JavaScript is a single-threaded environment that has to handle reads and writes and rendering, all in the type loop. So, if you want buttery smooth applications, you need to do 60 frames per second. And if you want to do 60 frames per second, you only have 16 milliseconds per frame. But the browser has to actually do work, rendering, and so forth. So it's common knowledge, let's say, that you only actually have 10 milliseconds to do all of your work. So all of your business logic and all of your generating data structure and everything, it has to fit in 10 milliseconds. If you pass 10 milliseconds, you no longer have 60 FPS, and your users complain because you just broke their mental model of the world. The only way to get 10 milliseconds consistently is if you switch to a one-way data flow. This is the version that's in ClojureScript. You can imagine how you would write this in other languages. Maybe. Notice there's core async. That's my one and ultimate channel. All of these events, all this raw data that comes into my system gets handled by this one queue. And this queue generates a data, right, based on my business logic, which generates a virtual DOM of how I want the data to be presented, which actually gets rendered in the browser. As long as you have this one-way data flow, it turns out that you can't enforce 10 millisecond rules. Because you know exactly what's going to happen over there at the end. So all you need to make sure is that any event that comes in, you need to make sure that core.async makes sure that it won't go over time. And if there's something that is going to take a long time, and there are many things that take more than 10 milliseconds, what you do is you say, that's all right, let's batch it. Let's do a little bit of work, and then send it back into the queue, right? And the next part of it will run again. And yes, this sounds complicated, but if you want to do computation-intensive stuff in a browser, and you want better smoothness, this is what you need to do. You need to switch to a one-way data flow. And the thing is, if you don't care about that, you just do it this way until you start caring about it, and it's really easy to switch. But again, it's all goes into this. I didn't talk much about the front end because I gave a talk at Tesla about it, so if you're interested in it, that's your third homework assignment. And I want to leave you one thing, because I didn't talk about REST APIs at all. So let's talk about REST APIs. REST APIs come from a time when there were backends and frontends. The problem is this is no longer true. Backends aren't backends, now they're multi-regional across the globe. All of your browser applications want to work offline, and all of your mobile applications have spotty 2G connections, right? And the thing is, your company is getting bigger and bigger. If you're the size of Facebook or LinkedIn or whatever, you cannot deal with the complexity of having all those developers creating REST APIs at the same time. And you want to ship faster and faster and slower and slower. So it's really interesting that so REST is dead. The reason REST is dead, as an example, is both Facebook and Netflix say that they're dead. And it's really interesting because Facebook is a monolithic application, right? They have one big monolithic application. And Netflix is this proponent of microservices. They have a very different idea of how the world works, yet they both, in secret, developed the same exact technology over 2 years and released it pretty much at the same time. And Netflix, that's Falcor, and Facebook, that's your GraphQL relay, right? And those are your buzzwords for Googling. And they both developed this idea that the only way to ship and to scale our systems and to make it all work is if we switch to a declarative query language and a single endpoint. No longer are browsers and mobile applications and your TV and whatever talking to a REST service, because a REST service is a coupling. It says that this is the way the world works, and when the world changes, you can't go and update every television set. But if you sit down and define a query language, something like SQL or Datalog or whatever, and you tell your clients that whenever they need data, this is the query language they use, and they just send it to this endpoint, you can change the backend every single day, and you can change your front ends and your mobile applications every single day. Because the API is the query language. And a declarative query language goes a lot further than a CRUD API. And if you're interested in doing this today, right, because these guys are talking a lot, but they're not really releasing a lot of code yet. If you want to do this today, you can do it like me. Because I use Clojure and I use ClojureScript. And I use Datalog as a communication mechanism between them, and I use Datomic on the back end, I use DataScript on the front end. You know what DataScript is? Some really smart guy went and ported the entire Datomic engine to JavaScript to work in the browser. You can actually use Datalog in the browser, you don't need to use ClojureScript because it supports a classic JavaScript API. So this is that notion that you need to start thinking about your front ends as an offline database that needs to be synchronized with the back end. It needs to, your views no longer talk about here's a collection of items and I'm going to render them. No, your views start talking queries. They say, I need the name of the fourth user that came into whatever, right? All of your friends that happen to have, I don't know, a Facebook profile or whatever, right? You need to start thinking about queries. And the way you need to start thinking about queries is if you realize that on your front end and on your mobile client, you need to have a database. And if you have a database on the front end, you have a database on the back end, you actually have to build a synchronization method. You need a way for one database to say, here's all the data you need to render, except for one thing. I don't have it yet, but I asked someone, and they're going to get it to you as soon as possible. Immutability changes everything, folks. It's not the end, it's just the beginning. That's all I've got. Do you have questions?